nanoHUB.org.
Online simulation and more for nanotechnology.
Today, in this second workshop of our 6-part nanoHUB series on hands-on data science and machine learning, we're going to look at how we can access some unique pieces of data using simple querying and APIs that have been created by a number of different platforms, how we can massage that data, and then hopefully after this session, using the tools that you've learned from it, you can apply this to maybe some machine learning models that if you stick around for the following sessions, you'll be able to get your hands on those as well. So let's get going. So to kind of motivate why we're doing these workshops, why we want to know more about data science and machine learning, it's a pretty ubiquitous tool in commerce, in finance. Your Google search suggestions or your Amazon preferences all have some machine learning algorithm sort of operating in the background. And they can be used for a number of different things like predictive models, classification of different pieces of information, or even dimensionality reduction to solve, higher scale problems. And even more interesting, they're being used in these sort of iterative loops for designs of experiments, where these models can tell you what the next best experiment is, and then you can iterate over that process to improve your models and have better predictive capabilities for what the next step should be. But again, we always come back to this idea that all of these models are built on data, and having that data centralized in some way is a key piece in gaining the information that we need in a quick and efficient manner. So there are a number of platforms that have started to be developed that are hosting these data repositories. So we host a number of tools and online simulation capabilities through nanoHUB, but there are a number of platforms such as Citrine Informatics, the Materials Project, OpenKim, and even Wolfram Alpha that are easy to access databases that have a wide array of data from materials properties to mathematical properties, and each of them, what unites them are easy to access APIs, things that allow us to talk to their databases and get that data out. So what does that look like for us? Well, we're going to kind of go through the steps for accessing each of these databases through these simple APIs. All we're going to be doing is some simple Python programming. After that, we're going to build on some of the tools and techniques that we learned in the previous workshop with Juan Carlos, where we're going to be using Python to massage this data to get the answers that we want out of it. I'll also like to note that we're going to go through kind of 2 examples of accessing different kinds of databases, and there will be a third example that's going to be very specifically geared towards some of the material scientists in the room. So what we're going to do is we'll go through those 2 activities, we'll open it up for Q&A, and then actually that 5th point in the outline we're going to shift down to kind of after the Q&A. So feel free to stick around afterwards if you want to do that. Okay, so let's get going. So the first thing that I need you to do, hopefully you've already done this, is you need to go to the Mat Data Repo tool that's on nanoHUB. Click this Launch Tool button, and we'll begin. So hopefully in the instructions that were sent out beforehand, you've already gone to at least this link to start with, and you've accessed the first notebook in the series of 4 that are included. And that'll be instructions on how to get each of your API keys for Wolfram Alpha, Citrine Nation, and the Materials Project database. Please have those API keys up and ready to go because we're going to use them in the following notebooks to actually access those databases. Okay, so here's the landing page for the Mat Data Repo tool. And like I said before, hopefully you've gone through this first link, so we're going to skip on to this piece here where we're going to do an introduction to querying. But first, I'd like to iterate that these API keys that you have, make sure that you keep them private. They are sort of a unique identifier to you, and make sure that you also follow the terms of use that are associated with each of these API keys. For the most part, you are free to query whatever data you want from these databases, with the exception that the Wolfram Alpha API limits you to 2,000 queries a month, which may sound like a lot, but you'll see very quickly when we start to get into the scope of these big data problems, sometimes we have to turn to other platforms for different pieces of information. So I just wanted to throw that little tidbit out there. Okay, so the first thing that we're going to do is kind of give you an introduction to querying these databases and show you what kind of flavor we need to go about through some simple coding to access the data that we're looking for. So the first database that we're going to use is the Wolfram Alpha. And I'm sure that some of you have heard of Wolfram Alpha when you were trying to solve a differential equation for your introductory calculus course. But they also have a really powerful search engine, kind of similar to a Google search, where you can give it string queries for certain things that you want to know about. So in our case, we're going to try and figure out, what are the melting temperatures of a couple well-known oxides. And then we'll do a little bit of plotting just to visualize that. And then we'll move on to the second database that's powered through Citrine Informatics on a platform they call Citrine. And again, we're going to do a simple query with their API to, say, extract the band gaps of a number of different materials. And then we'll do some visualization with Plotly. In addition to that, one of the things that's powerful about Citrine is the ability to access other people's data, but you can also upload your own data to share with the community. And I'll go through the steps on how we do that and what their interface looks like. All right, so let's go back to the tool. So now that we've landed onto this first page, this miscellaneous querying, we're first going to load in our API key. So like in the previous workshops, anytime you're in these Jupyter notebooks, it's a simple Shift-Enter to run through the cells, or you can hit the run command up here. I prefer Shift-Enter because it lets me do a little bit less work. All right, so the first thing we're going to do is we're going to load in our Wolfram Alpha API key. So again, I mentioned that these keys are unique to you and you should not share them. So I'm going to move my screen off to the left real quick while I upload my key. After you upload your key, simply press Enter to have your key stored. And after that, you should get a little success message that pops up. All right, so I've entered my key, I've pressed Enter, and now I'm going to move on to the Citrine API key. Press Enter to store your key, and now we can move on to the rest of the notebook. So, like any Python script, we're first going to import a handful of libraries. So the first ones that we're going to import are the libraries that are unique to Citrine, as well as this Citrine data retrieval class that will allow us to use our API key to access their databases through a simple object command. We'll also import the Wolfram Alpha module that we can also use its class that's embedded within there to use our API key to then perform a simple query. And we'll import some miscellaneous tools for plotting and data massaging. Here is where we're actually storing our API key as this API key variable, which we'll input to the class that we'll define below. All right, so the first thing that we're going to do is we're going to figure out what information is on Wolfram Alpha at a quick glance. Now, we could just go to Google and put this into a search bar and get some information out of it, but as soon as you start to scale up the amount of data that you have, it's a lot easier to have the computer do the heavy lifting for you. So I'm going to show as a simple example of querying 4 oxide materials that we want to know the melting point of. But this can be extended to whatever problem you specifically want to look at. Okay, so the first thing we're going to do is we're going to create this client object out of this client class from Wolfram Alpha. We're going to insert our API key into here, and now we have something that we can actually use to query their databases. So what we're going to do is we're going to create this empty list here that we're going to call this temp list. And then we're going to query over 4 different oxides. So Al2O3 and Cr2O3 are 2 well-known industrial oxides that are used in a number of applications. They're also very stable. And maybe we want to look at, for fun, a radioactive oxide like plutonia, or even a more advanced or exotic one, you could say, hafnia. So what we're going to do is we're going to iterate through this list in a for loop, where for every single one of these strings, we're going to concatenate it with this queried search of oxide plus the melting point. And we do that by taking this client object that we created here, and all we're going to do is say client.query, and then the string that we want to query. So again, a very, very simple query. Shift-Enter to run the cell. And what it'll return is a string value of the results from the query. So what we're returning here is that the melting point of Al2O3 is 2040 degrees Celsius, Cr2O3 is 2435. Now, since this is a string, it's not a floating point number. We prefer floating point numbers when we actually plot our data. Otherwise, Python's going to get a little mad at you. So we're going to kind of get rid of this extra stuff at the end through simple string deletion, and then we're going to convert that number to a float. Once we have it converted to a floating point number, we can append it to a list, and then we can start visualizing the data and doing some cool stuff with it. So this cell has been run successfully, and now we're going to plot the results really quick. So we're going to import a library called matplotlib, which is sort of the Python flavor of plotting from MATLAB. And we're going to create a simple bar chart here where we're going to take the query list that we defined up here, and we just want to plot the melting temperatures that we've gotten from this simple query. We're going to enumerate over that list to create some labels, a little bit of advanced plotting that if you want to take the time to really understand what's going on here, I encourage you to come back to the lectures after the recordings have been uploaded. And you can also follow along in your handout if you feel like you're falling a little bit too behind. But we want to make sure that in the interest of time that we get through the workshop. And if you have any questions at the end, feel free to ask either online or send us an email afterwards. We're happy to help in that regard. Okay, so Shift-Enter to run the cell, and we should get this simple plot down here of the oxide melting point and our queried oxides. And as we can see, there's a range of melting points that we have from them, but at the end of the day, it seems like Hafnia is the winner, if that's the one that we wanted to stabilize for a certain application. Okay, so we've performed a very simple query with Wolfram Alpha through string queries, but what if we can do something a little bit more advanced? So let's move on to Citrine. Citrine is a database platform where people can upload their data to be freely available. You can choose to keep it private if you'd like, but in the sense of a community, it is nice to distribute your data if you're going to be accessing other people's data. So what we're going to do is we're going to do something very similar to the Wolfram Alpha process, where we're going to use this Citrine data retrieval class with our API key in tow, create this object that I've decided to call a CDR. And down below, we're going to, instead of saying query, we're going to say get data frame. Now this command is going to pull a pandas data frame from the Citrine database with the unique ID 172242. Now this number will be unique to whatever database has been uploaded to their website. And you can find a number of examples here in the block I've highlighted. But I'll also show you when we can go onto their website, we can look for databases that we're interested in. Okay, so now that we have our API key and we've created this class, I want to create now a data frame from this set. So Shift-Enter to run the cell, and we're going to perform our first query of the Citrine database to get some band gap properties. All right, so now that it's been completed, you'll see that you have a number of chemical formulas for each compound. You have the reference that's associated with that value, and a number of band gap properties. So what does this look like visually? Well, instead of using matplotlib, matplotlib is very advantageous when you're trying to create publication quality images, but they're static. The advantage to Plotly and using them with these Jupyter notebooks is you can interact with them. You can hover your mouse over, you can see the values. And the advantage to sort of marrying Plotly and Pandas data frames together is instead of saying something like, I want to plot the first and third column of my data frame, I can simply say, in this Plotly image that I want to create, I want to use the Pandas data frame that I defined above from my query, and I can now call these column headers, the chemical formula, and the band gap. So Shift-Enter to run that cell, and we should get now an interactive image below. All right, so here is a collection of band gaps for a number of different materials, all with literature references and sourced from the Citrine database. And now you can hover over them to see what the individual band gap measurement is. You'll notice that a number of these bars have two different values, and this would come from two different measurements of the band gap. There are a number of different methods to go about this through absorption techniques or other more advanced spectroscopy that I'm not an expert on, but maybe some of you in the room can speak on. But at the end of the day, what we have is a plot that you can very quickly hover yourself over and look for different band gaps of materials. You can even zoom in on pieces of the plot that you're more interested in. And you can always reset that by going up to this Reset Axes command. Okay, but what if we're not exactly interested in the band gap? What if we're interested in, again, say, the melting temperatures of things? Well, we have an example here that's the melting points of the periodic table of elements. So let's perform just another quick query by replacing that number. Shift-Enter to run the cell again. And now, instead of plotting the band gaps of a bunch of different materials, we're going to plot the melting temperature of the periodic table of elements. So you'll see that it's a little bit of a larger query since we're looking over more compounds. But now here we have all the citations for each of the elements, the melting temperature, and now let's plot it. Okay, So cool. We have the melting temperature for every element that's in the periodic table. Again, you'll notice that a few of these numbers have multiple measurements associated with them. So that could be the way that it was actually done in the experimental setup is going to give you some variation in your results. But it's consistent with our ideas that we know that things like tungsten, tantalum, those are going to be the elements with the highest melting points. So I mentioned that one of the powerful things about Citrine Nation is in addition to accessing other people's data, you have the ability to upload your own databases to their server. This is definitely an advantageous piece of science and engineering where your data no longer has to be stored on your hard drive until someone asks for it. You can distribute it through the community. They can access your data, maybe make predictive models, and they might think that your data is so cool that you're going to get cited in a lot more ways than you previously thought by just publishing your paper. So anytime you want to add data to the Citrine Nation database, you can go to their website and you can go to this Add Data piece that's at the top of the window here. All you have to do is create a database name. So you could create a test database, some description that's unique to what you're uploading. And then you can upload something like a CSV or an Excel spreadsheet that they can then kind of get back to you. And they'll go through an iterative process with you, a member of their team. They'll say, okay, maybe you should relabel this, or I want to double check one of your references here to make sure that the data that you're uploading is validated in some way. If you so choose, you can keep this data private, and only the company, Citrine, would be able to access your data for maybe some of their goals and intentions. But it's a good way to sort of centralize the platform. I also mentioned that these examples are just a small list of some of the databases that are available to you. So if you're ever curious about other things that are on there, you can go to this data sets area. And you'll notice now that we have a number of different databases with a unique ID associated with them. So maybe you're interested in the mobility of certain materials. There are going to be a number of databases that are curated for that. Maybe you're interested in the diffusion properties of materials. And there are going to be a number of those kind of databases as well, with certain elements or certain diffusion properties with them. Okay, so now that we've gone over the Citrine Nation database, we're going to move on to the second activity. A little bit more of an advanced query, but we're going to do something a little bit more exciting. We're going to kind of give ourselves a secondary motivation. So I want you to picture this for a quick moment. You have a client, let's say you're working for a consulting firm, or you're in some industrial application where your client or boss wants you to develop some kind of an oxide scale for a process or some kind of material that it wants to be stabilized. And we kind of have an intuitive sense that oxygen is all around us. It bonds to surfaces and substrates very, very readily. And so we know there are a huge number of potential oxides out there that we could use maybe for this application. So maybe there are some figures of merit that we want to kind of use to narrow our search down. Maybe the reason that we want to stabilize this oxide scale is because we want to have a surface that has a close packed ionic structure to prevent further oxygen getting into your surface, into your material, making it break or become brittle. And let's say you also want to have some kind of a stiffness characterization to it. So you don't want it to be too soft. So what we can do, there are a couple of different ways that we can approach this problem. We can look for different stability criteria, which oxides are the most thermodynamically stable. But it's good to note as well that sometimes metastability is a desired property. Diamond, for instance, is a metastable compound, but we know that it exists readily in nature and around us. And so then we're going to use some of these ideas of stability, different types of stiffness data, and we're going to try and figure out, okay, what's the best candidate for my search? So we're going to turn to the Materials Project. And the Materials Project is a database that is based on density functional theory data. We don't need to get too much into the physics of how those calculations work, but at the end of the day, what DFT does for us is it calculates ground state structures and predicts energy stability of certain atoms in whatever crystallographic arrangement they have. The Materials Project database also boasts an amazing API querying system that allows us to perform these huge queries of an ever-growing database and then perform very quick filtering through Pandas data frame operations where we can kind of convert between different types of data. And then after we have that data, we're going to figure out, well, what's our best candidate? And so we'll go through each of those steps one by one. I'm going to warn you beforehand that some of the blocks that we're going to go through have some chunky pieces of code in there. But again, if you feel like you're falling behind, these lectures are recorded. You have your handouts to follow along with, and we'd be happy to stick around after the Q&A or address questions that you might have moving forward. Okay, so let's sort of do this large-scale querying now of the materials project database. So we're going to go back to our landing page, and we're going to go to this third Jupyter Notebook link. Similar to the other two notebooks, the first thing that we're going to do is Shift-Enter our way down the cells, and we're going to upload our materials project API key. So again, I'm going to move my screen over real quick out of your view. Paste your key into the cell and press Enter to upload. All right, now we're going to import the PyMatGen, which is the library that is associated with the materials project. It stands for Python Materials Genomics Package, and they provide a number of tools for quick querying and accessing of data on their servers. And then again, like before, we're going to import some miscellaneous tools for data processing and a little bit of visualization. Here is where we're going to use this MP-Rester class with our API key from the materials project. Very similar to the process that we set up for Wolfram Alpha and Citrine, where we create this rester object from this class, and then we can use that to perform our simple queries. Except this time it's not going to be as simple of a query. Instead of asking for a simple string or just pulling an individual database, we're going to ask the materials project database through this rester.query command. I want basically any compound that is containing an oxygen atom in its system. And the properties that I want to extract from you are the unique materials project ID, the chemical formula, the volume of this crystallographic cell, number of elements. This E above hole it stands for the energy above the convex hole, basically meaning a stability criteria. If the number is 0, it's the most stable structure that we can have. If it's anything above that, it may be a metastable structure. Again, you don't need to get too much into the physics of that for the people in the room that want me to move past the materials examples, but what we're going to use this as a sort of filtering criteria to parse down our data into something that's a little bit more applicable to us. So Shift-Enter to perform that query, and pretty soon you're going to notice that the database that we're querying is going to be very large in scale. So I mentioned that the Wolfram Alpha limits you to 2,000 queries a month. Right now, on the fly, we're going to perform 60,000 queries from the materials project database. And each of these is going to have an oxygen-containing atom in its crystallographic structure. And each of these is going to have sort of a unique orientation to it. Some of these may or may not have mechanical property data associated with them. And we'll use that as we sort of kind of continue to filter down our data. And then we'll do some advanced plotting after we get through that. So what we're returning right now are essentially dictionaries. And if you attended the first workshop, will know that dictionaries in Python are key and value pairs. So for every query that we're doing, it's going to return to us a dictionary of each individual compound with the properties that we wanted to extract. So let's look at an example of one of those queries. So first you'll notice that we have our 60,000 queries to look from. And if we access one of them sort of at semi-random, we'll see that we have this Bi2O3 compound. It has a defined volume with it. And we'll notice that this E above hole parameter is in fact not 0. So what we've extracted here is something that is deemed to be a metastable structure, and it may decompose into something else given enough time. We'll also notice that this elasticity parameter that we've queried, it does not have any mechanical property data that's been calculated for it. There are tools and ways that you can calculate these properties, and the Materials Project team offers ways for you to upload your own calculations to increase sort of the scope of what the database has to offer. It's a little bit more involved than the accessibility for uploading things to the Citrine database, since you actually have to perform your own DFT calculations. But if you want to know more about that, I promise I don't work for the Materials Project, but they are an amazing team to work with, and they're very responsive to problems. All right, so what we wanted to do, again, I want to remind ourselves that our boss wanted us to find some of these oxides. So we now know that we have 60,000 to choose from. And let's say that we want the most thermodynamically stable one, and we want to figure out what the ionic packing fraction is, or how densely packed these atoms are based on their ionic radii. And we're going to use a couple of those filtering criteria sort of at once to take our database from 60,000 to something that's a little bit more manageable. So first we're going to filter for energy stability, and we're going to calculate the ionic packing fraction of our materials sort of on the fly. So Shift-Enter to run through the cells, and this is where we're going to define that energy cutoff value. So if any of our E above hole parameters are greater than 1 millielectron volt, the units that are returned here are electron volts, so I want something that is less than 0.001 electron volts. All right, so Shift-Enter to run through that. And what we're going to do is we're going to create a number of dummy lists to do some sort of calculations on the fly. And we're going to take this giant dictionary that we have of all of our queried compounds, and we're going to filter out the ones that don't meet that energy criteria, and we're going to create a new dictionary out of that. Once we have that dictionary, we'll do a little bit of expansion of the different materials, and eventually the goal is to get everything, into a pandas data frame. Once we have that pandas data frame, it's a lot easier to access our data, visualize it, and perform some cool operations. All right, so what we're going to do is we're going to do a loop through all of our data to start with. And to begin with, we're going to basically say we're going to access the key and value pair of the energy above hole parameter that's in this dictionary. So we're going to get the value that's associated with this key. And if it's greater than this energy cutoff value that we defined, we're just going to skip it, and we're going to move on to the next piece of data. Once we've moved on to the next piece of data, we know that it's something that at least meets this first requirement for energy stability. So that's one filter that we've applied kind of on the fly. Okay, so now that we have that, I want to basically take all the parameters that I'm interested in, so the density, the formula, the elastic properties that I want, the volume, and I'm going to start pushing that into another dictionary that we'll get to down here at the bottom of the cell. But for now, I want to now calculate the ionic packing fraction. So how do I do that? Well, first I have to figure out what atoms are in my system that I've pulled in this query that I performed. So we're going to go through and basically extract each of the elements and their associated types. Once I have each of these elements, I'm going to perform a really simple query of the ionic radius for each of those elements. If you were in the first workshop, this code is nearly identical to where we created a list of all the elements from the periodic table, and we queried for properties like the melting point or the Young's modulus of a material. So we're going to do the same thing, where for each of these elements, we're going to query the ionic radii. So here we have this element object dot average ionic radius. What we mean by average ionic radii, for those of you that are familiar with chemistry or basic material science, depending on the oxidation state or the coordination number of an atom, it may have a different formal charge. That formal charge will define how big or small that relative ionic radii is. We're going to query, instead of every individual oxidation state or every charge state, we're going to sort of say, well, what's the average of all the compounds that exist out there? How often is this element found in that state? And it'll perform sort of this averaging on the fly through this query. Once we have that, we're going to append it to this list of our radii values. Now, once we have the atomic radii, we wanted to figure out, well, what's the ionic packing fraction? And we can define that by the amount of volume that our atoms take up, or our ions, and we can divide it by the total volume of the cell. So we're going to convert all of our radii into volumes. And then now that we have the volume of each atom, we can sum up all of our atoms to get a total atomic volume. And then we're going to calculate this packing fraction, or this ionic packing fraction. And once we have that, we're going to push it into a dictionary with all the other values that we queried from before. So again, all these calculations are being done on things that originally met our energy stability criteria. So Shift-Enter to run through that cell. And it's going to do all these calculations for you. It's going to take a little bit of time since we're going through 60,000 iterations, but it should be done in just a few seconds here. So the next thing that we're going to do is you'll notice that we created this dictionary and we have sort of this list that's stored within the dictionary as the value for the key that we've created as the materials project unique ID. But it's often easier to work with things that are data frames instead of dictionaries. So in this cell, we're going to pull everything out of our dictionary, push it into lists. Once we have those lists, we're going to convert everything to a NumPy array. And after that, we'll push it into a data frame. There are a number of ways to push things from dictionaries into Pandas data frames. You might be able to see my code here and say, I could do that in 4 lines less than you have here. And you're absolutely right. This is just an example of one of the ways that we can massage the data. I'll never claim that this is the most efficient way, but I think it illustrates kind of exactly what we're doing explicitly rather than kind of packing everything into more well-defined functions. All right. So once we have a Pandas data frame, the advantage to Pandas data frames is it gives you the visualization capabilities of an Excel spreadsheet while still having the accessibility and the computational power that is built into Python. One thing that you'll probably notice pretty quickly is that now all of these values that we've calculated, we have very well-defined stable structures, but you'll see that this elastic tensor property, or these mechanical property data points that we're interested in, a number of these have not returned values, meaning that the DFT calculations on this crystal structure haven't been performed. They may be performed in the future, but as of today, when we've queried the database, they don't exist. So let's get rid of those values. I'm going to skip through a couple of these cells a little bit quickly in the interest of time. But what we're going to do now is we're going to filter for this elasticity parameter. So for any of the cells that had a none or NaNs, basically meaning that the data doesn't exist, we're just going to go through and we're going to delete all of those rows. So Shift-Enter to run that cell, and now you'll have a more compact and dense data frame to work with all of the unique materials project IDs, their chemical formulas, and now the elastic tensor and ionic packing fraction. So these properties that we're a lot more interested in for figuring out what's the next step moving forward, how can I deliver something that's within the scope of reasonable oxides for my boss or my client. Now you'll notice that these mechanical property data, this mechanical property data, is still in a dictionary. So I want to be able to plot this a little bit easier. So I'm going to take all those values and I'm going to kind of push it out to individual data frame columns. But first, let's see how well we've reduced the scope of our problem. Recall that we queried every single oxide that exists on the database, and we returned 60,000 different parameters. Now we have only 855. So that's a much more reasonable problem to attack. We have 855 oxides to consider, and after we do a little bit of visualization, we might see that we can even narrow this down to 50 or 100 parameters that we're looking at. Okay, so first let's expand everything from our dictionary into individual data frame columns, where we're going to create some empty lists for our bulk and shear modulus. Perhaps some other material properties that we're interested in are the Poisson ratio or the anisotropy of the material. For every dictionary, we're going to go through and I'm going to append the value of each of these bulk, shear, and other mechanical property data to lists. And then like before, push it into a NumPy array, and then create a data frame from that NumPy array. So now I have a unique data frame for my mechanical properties, but I want to keep everything contained in one place. So I'm going to concatenate my original data frame of queried values and my elastic property data here. This step we're going to kind of gloss over. Basically, there were some values that were queried that were a little bit erroneous, so we're going to remove them. They didn't make physical sense. And I'm actually interested in looking at those couple numbers a little bit more closely. But for this example, we just need to know that we're getting rid of some values that didn't quite make sense from a physics point of view. Okay, so now we have our completed data frame. We have the materials project IDs, we have our calculated ionic packing fractions, and now we have mechanical properties to work with as well. So let's do some advanced plotting to kind of sink our teeth into what we're working with here. So we're going to use Plotly. We have a lot of data to look at, and it's a lot easier if we can create something that's interactive, something that we can hover our mouse over and see, what am I actually looking at here? So just like before, we're going to import the libraries that are associated with this code. If you were here for the first workshop, we're going to be building off some of the knowledge that was done there. Otherwise, the basics of any Plotly image are creating your layout that you can customize here. So this is where you can create your titles, your font family. I'm a big fan of Times New Roman, but maybe you prefer Arial or Georgia. You can look up the documentation for Plotly. There's a number of customization options that you have in here to create plots that are tailored towards your specific flavor of problem. You can also change the height, width, things like that. Okay, so now we're going to perform a little bit more of an advanced plotting scheme with kind of, again, marrying the two of Pandas and Plotly to do something very powerful. So the first thing that we're going to do is create a trace of all of the data points that we have in our data frame. Now, instead of saying I want to plot the 5th and 7th column, let's say, I can just quickly access for all of my X points, I want to plot the density. And I can just say dataframe.density. And I want to also plot the ionic packing fraction. So just dataframe.ipf. Here, you can customize the markers. So you can make the color change. You can change the shapes, the sizes. You can add little circles to the outside or X's within. Again, a lot of customization options here, but we're just going to do something kind of simple. And then for the text, the power of these Plotly images in these Jupyter notebooks is I can actually have the chemical formula that's associated with that data point show up when I hover over the point. Now we're going to do some advanced Pandas logic to sort of compare to, well, what's out there that we know very well. So again, I mentioned that maybe we want to design this oxide scale to compete with well-known oxides like Al2O3 or Cr2O3. So what I want to do is I want to plot those specific points from my data frame. But I don't really want to scroll through 855 different compounds, get the X and the Y component, and do that by hand every single time. So what I'm going to do is I'm going to create another scatter where in my data frame, my df_oxide, I'm going to perform a logic operation where I say, I want you to find me the formula that's associated with this compound, and I want you to make sure that it's the most stable structure that I can find, meaning that this energy above convex hull is 0. Once you've found that, I want you to locate for me the density that's associated with these two logic operations. So you can think of it as we're going down this list. We find Al2O3. We also find where this E above hull parameter is 0. Once you've found that, I want you to give me the density. We'll repeat the same thing for the ionic packing fraction. It's the same bit of logic here, but instead we're going to locate the value from the ionic packing fraction column. Again, this can be unique to whatever data set you're working with, but the bottom line is we can use quick logic operations to plot something from our data instead of having to go through by hand. I'm a big fan of letting the computer do the work for me, if I give it the right code, of course. So we'll do that for a couple well-known oxides. We'll create our traces together, and then we'll plot our final image. So now we have this sort of interesting looking scatter plot where you might notice there are sort of 3 bands of regions that form. We have our Cr2O3 and alumina compounds that we see have a relatively high ionic packing fraction, but there are a number of compounds up here that may be more interesting to look at, like this lithium copper or this potassium niobiate. Whether or not those are the oxides that you want to consider is kind of, again, up to your specific problem. But maybe we want to go back and say, let's do something a little bit more advanced. I want to look at kind of how all the mechanical properties play with each other. So we're going to go through and create another image where we're, again, importing the Plotly library, creating our trace here, and I want to look at first the relative comparison between the bulk and shear modulus. What those properties are for the non-material scientists in the room isn't super important, but what we'll show is that there is a very linear correlation between each of these data sets. Now, rather than making just a bunch of black scattered points, I can actually do something a little bit more advanced, and I can make my color scheme of each of these markers associated with one of my other material properties, essentially adding a third dimension to a 2-dimensional plot. So what I'm going to do here is create another trace where I'm going to grab the bulk and shear modulus of, the shear and bulk modulus of each of my materials. Again, using the chemical formula as the text that will show up when you hover over. And now instead of saying color equals black or red, I can actually make it one of the columns from my data frame. Here I want to make it the Poisson ratio, which is a relative comparison of how much something stretches in one direction versus the other. Again, the physics we don't need to go too much into, but what you'll notice pretty quickly is that there is some kind of a trend here. So we can see very clearly that there's a linear trend between the bulk modulus and the shear modulus. And as we kind of shift our way up here, it seems like our Poisson ratio also gets higher. So that may or may not be interesting to your problem, but I think it is very powerful that we can essentially create 3 different dimensions on a 2D plot. Okay, but again, let's go back to we wanted to create an oxide that has a high ionic packing fraction and perhaps some kind of a stiffness that's above a certain parameter. So we can do this on the fly. Let's change our plot to be the bulk modulus versus the ionic packing fraction. I'm going to change these things just so I don't get myself confused. IPF. And now, instead of plotting the shear modulus on the x-axis, I'm going to plot the ionic packing fraction. Again, all we have to change is the column header that we're pulling it from. Replot our image. And now we have something that's kind of interesting. Again, from the ionic packing fraction, we see that we have these sort of 3 distinct regions that are popping up. But let's say that we wanted to consider something, if we recall, that these compounds that are the well-known industrial oxides had an IPF of around 0.3. So maybe we only want to consider compounds that are up here. And maybe we want to consider something that has the highest stiffness and the highest ionic packing fraction. Well, it looks like it's this PaO3 compound, which unfortunately is radioactive. So your boss may not be happy that you came to him or her with a radioactive containing oxide, so maybe that's an additional filter that you want to apply. Again, we can do this through simple data frame operations and parsing our data down to the problem that we're the most interested in. Okay, so that concludes the second piece, the second activity in the querying exercises. So what we're going to move on now is to the Q&A session. If you'd like, I'd like to reiterate that if you are keen on learning something that's more material science focused, we'll do an exercise in activity 3 where we will query and actually plot some phase diagram data from the materials project database. So to then reiterate before we move on to that, I guess, and to the Q&A, these databases that we've accessed, they boast simple API querying capabilities that allow you to both access other people's data, and they provide you tools on how you can upload your own data. At the end of the day, all these machine learning models are built on data, and now that you have the tools to access that data and create your own data sets, I hope you stick around with us for the 3rd and consecutive lectures where you'll learn how you can use that data for predictive models or classification or dimensionality reduction in your experiments. So with that, I'd like to thank you all for sticking around, and we'll open it up for Q&A. And again, if you'd like to stick around after the Q&A session, I will be here past the regular hour time slot that we've associated for this, and I'd be happy to take your questions.
So does anyone have any questions? If not, then I'll start with one question. So, Zach, we queried for the oxides in the materials project example. Is there a simple command that will let me know what is available on materials project without having to go to the website and click on things and see, oh, they have elastic properties, oh, they have band gaps? Is there a function that we can say, list all the properties that are available for this material? Is there something like that?
I believe there are. The syntax of it, I don't know off the top of my head, but what I will say is that with the materials project, they do offer quite a bit of documentation on their website here. So this pymatgen.org is where they have all their documentation for the querying tool that we were using. So a number of properties that do exist, I think, I won't waste all your times going through the documentation itself, but there are easy ways to figure out of these which properties there are.
Thanks. And there's a question from the chat here. Can we search the XRD data?
Absolutely. So I think it's good now to kind of show a little bit of what the materials project has and why it's a little bit easier sometimes to access it through this API. Where on the materials project, after you created your account and logged in, if you're interested in something, you can basically kind of click through the different elements that you might be interested in, and a bunch of different compounds will show up for you. So again, there are these formation energies, this E above hole parameter. But if we look at something like this Fe3O4 that popped up first, it'll have a number of bandgap data material, XRD, and those things can be easily queried from the materials project database. The commands for them are going to be a little bit different, and I can send or include links for where that documentation is. But again, it's going to come down to kind of reading through the documentation for PyMatGen. But anything that's on this website that you see here can be queried through a simple one-line command.
I hope that answers that question. Anything else from anyone else?
Hi, can you hear me?
Yes.
I have two questions. One is related to today's presentation, and another is not related to today's lecture. So, can I ask something that's not relevant to today's lectures?
Unless you're setting me up for failure, absolutely.
No.
I'm kidding. I'd be happy to help.
Okay, so my first question is actually not relevant to today's lecture, and I actually wanted to ask this question on the first lecture, but I forgot to ask it. So I was actually doing, I'm using machine learning for my experimental purpose, and I am doing something called Q-learning. So I was wondering, during this lecture series, will you discuss anything regarding Q-learning?
So not specifically Q-learning, but in the final workshop, we will go over some techniques that are called sequential learning.
Okay.
Where they basically, you can, based on the data that you have, you create a model that tells you what your relative uncertainty is, where you think you might have, where you might be lacking data. And what these models will tell you is basically, based on your data, how can you either reduce the overall uncertainty of your model, how can you get more information from a spot that may be kind of a dark zone. But perhaps Saket or Juan Carlos, they're the ones that would, I think, be a little bit more knowledgeable if what we're doing is similar to this Q-learning method.
Yeah, I can jump in real quick. Q-learning, if I remember correctly, is a form of reinforcement learning. So this session, this series won't really cover that. The reason for that being that we kind of tend to stick to things that we use day to day. Q-learning just doesn't happen to be one of those. But if there's enough interest for Q-learning and we happen to use it regularly enough, then we invite contributions and we can cover it at some later time. In this series, we won't be covering Q-learning as we felt that that's a bit of an advanced topic. We wanted to get everyone, especially experimentalists and people who are generally not doing this day in, day out, on the same field and get the basics ironed out and get them all to a place where they can know exactly where to go and know exactly what to do to start training models, and then they can pick up from there on.
Okay, I got it. So basically, like, see, for my experiment, it's like has to be live. Means like what will be my next test that will be determined by the machine learning. And actually, I didn't do that work. Like my collaborator did that work. So I am basically a beginner. So I was thinking, and that part was kind of difficult for me. Like he was doing things for me, and we collaborate things for this project. So I was thinking, like whatever the basic, I should start from there. So, do you think if I like watch this lecture series, that will be helpful for me to understand that reinforcement learning later, or do you think it's completely different track? Because I can see one thing that you guys are doing, like you have some specific data or a static data, and based on that data, you are plotting something or taking some decisions. But in my case, it's like has to be continuous, like one experiment, and second experiment will be depend on the first experiment, third experiment will depend on the second experiment, something like that. Like it has to be live and continuous.
Absolutely. So, as far as relating models with experiments go and using models to guide the experiments, that's where the sequential learning part of it comes in. And the intention of this series is, like you said, to cover some of the basics and hope that people like you and many others who are working in collaborative projects can get a basic feel for what exactly happens behind the scenes. They don't need to write code from scratch. We have starter codes available. If you're interested in coding it up yourself, we have the environments ready for you to use. But if you're in the position where you're collaborating with someone and they're providing models to you, this is a good platform to you to understand what are the basics behind it. And then you can slowly graduate to Q learning or whatever fancy learning, machine learning algorithms that you use. What we are covering here is kind of standard run of the mill. Most projects would do this every day. The sequential learning, the last part, is a little advanced. It involves, again, coupling things with experiments and all that. And obviously, all these methods vary, all the data sets vary for each research area. Because we are a materials group, we usually focus on materials databases. But if you're working in another field with another popular database, I think all of these techniques will transfer reasonably well. So you should be able to swap in once you have gone through these lecture series or these hands-on demonstrations. You should be comfortable enough to swap out maybe one piece of code with another data set that you like or something like that. That is the point of this series, to enable you to do that. Of course, there are many details, there are many specifics that only you will know because you are the expert in that field and not us, but hopefully this gives you enough of a starting point.
Okay, I got it. Thank you. And the first and the question that's related to today's lecture is really silly question. I missed the first part. How do you find that key? Like because I could not run any of the code because I missed the first part to get the key.
Oh, okay. So to get your keys, that's going to be on each of the. Let me pull up. So for each of the databases, they're going to have their own API keys associated with it. So if you go to this first notebook in the tool, you can scroll through it, and I provided links for Materials Project, Citrine, and Wolfram Alpha. You basically go to each of those websites, create an account, and you just ask for an API key, and they'll give one to you.
Okay, I got it. Thank you.
From a couple things in the chat, I first wanted to thank Nicholas for getting extra credit and helping us out in here, and also for calling me out on my PA comment. That's good to know. And yeah, with the Materials Project, yeah, it's a vast database. So most everything on there is going to be calculated, but something like Citrine kind of has a hybrid of both calculated and experimental properties. And anytime you query a database, it'll be clear which values are coming from which method, and they'll provide a DOI and a reference for you there.
Great to see all the interest. Any other questions for Zach? If not, Zach, I believe, has a third optional, highly specific materials problem that involves some very cool plotting and querying that he wants to get into. So if you want to stick around for that, please do. If not, feel free to leave the session. But before anyone leaves the session, I request everyone to unmute themselves and give a big hand to Zach for introducing us to this new world.
Awesome. Well, thank you to everybody that joined us today. If you're taking off now, feel free to come back for the future sessions and stay safe. For those of you that are choosing to stick around, you get extra credit, and we'll go through that final piece of the Jupyter Notebook where we're going to, again, query the materials project, but instead of just kind of getting some oxide sort of data, we can actually do something kind of cool where we can say, based on the data that's up there, they actually can create calculated phase diagrams. And what we'll do is we'll go through basically saying, for a combination of elements, we can create sort of binary formation energy figures, as well as ternary and quaternary phase diagrams sort of on the fly. So if this is something that you're interested in for your research, maybe you want to look at a couple different elements and you want to at least know, where do I start? Which ones are stable? Which ones are the relatively ground truth structures at 0 Kelvin? Again, Materials Project is a vast database, so none of these values are really going to hold for what's the ternary phase diagram at 1,000 degrees Kelvin or 1,000 Kelvin. Something like that would be a little bit more up thermocalc's alley. But without further ado, let's get into the third notebook, since I know many of you have other places to be. Okay, so just like before, Shift Enter to run through the cells, get our API key sorted out. All right, so what we're going to run through here is essentially we want to figure out what are the stable structures or what are the compounds that can form for a given combination of elements and what those structures look like in kind of the binary, ternary, and quaternary phases. So just like before, we're going to install a number of libraries, get our API key, and we're going to create the rester object to actually do the querying for us. So what we're going to start with is a simple list of 4 elements. I've chosen these 4 because I looked ahead of time on the Materials Project database for which quaternary phases they actually do have stored. This was one of them. At any point in time, you can change out these element lists here. So we could perform a secondary query where maybe you were interested in aluminum, cobalt, and maybe something like platinum. And then what this block of code is essentially going to do is create how many combinations of 2, 3, and 4 you can make from whatever list you create here. So you can do something, as large or as small as you want. For now, we're just going to do these 4, and then we'll run through this cell. And what this is going to do is it's going to create every binary, ternary, and 4 element combinations from our list of 4. So what those outputs look like is something like this, where we can essentially create 6 different binary compounds from this list of 4, 4 different ternary compounds, and only 1 combination from 4 for our quaternary. And what this is going to do is it's basically going to concatenate all these elements together into strings, and we can use those strings and ask the Materials Project database, what does the phase diagram look like for this combination of elements? So let's go through and run that. We're going to create this empty dictionary that I'm going to call a binary dict. And what we can do basically is we're going to create a whole bunch of these phase diagrams or these stability figures for the binary case. And once we have things that we know are stable structures and they are a binary, I'm going to store them in an additional dictionary. And we can basically say now, I want to now perform an additional query. Maybe I want to get some properties out of it like the crystallographic structure or the atomic positions. And I'll show you how to do that in the cell below. But essentially what we're doing here is we're going to loop through each of these combinations that we created of the binaries. We're going to perform this quick query where we're going to get these entries. And once we have that, we're going to create a phase diagram. This phase diagram is created on the fly with functions that are built by the Materials Project team. And then what we're going to do is we're just going to display that. After we have each of these data sets, we're going to sort of push everything into a dictionary based on it being stable. We again kind of go back to this energy above the convex hull criteria. And then I've created a simple little filter that if the chemical formula is above a certain length, we know that it's a binary. There are other ways to do it, but this is just kind of the way that I decided to go about it for this quick example. So what this is then going to do is it's going to say, okay, for the cobalt-silver phase diagram, we see that the formation energy remains at 0 for every mole fraction that we can consider, meaning that this compound will not form a binary, or at least it hasn't been calculated on the Materials Project database. I can't speak for the entire cobalt-silver system, but this at least tells me that the data isn't here for this system. But if I move on to something like antimony cobalt, we see that there are actually 2 intermediate phases that form depending on the fraction of cobalt. And we can see the formation energy that's associated with it here. Again, for cobalt, we see that cobalt oxides can form in 3 different stoichiometric compounds. antimony silver apparently doesn't form. We know that silver oxidizes pretty readily. This red point here, I'd like to note, is a metastable structure. So there's a crystallographic structure on there that actually made it past one of our filters here, where you can show different unstable criteria. So here we've made it a pretty small number, so we shouldn't be getting any wild compounds there that are going to decompose pretty readily. But this number can be sort of changed at liberty. Okay, so now that we have all these structures, again, we sort of pushed everything into this dictionary. And now that we have this dictionary, I want to perform some additional queries. So I'm going to take all those structures that we had, that we know are binary compounds, I'm going to push them into sort of another dictionary to access later. And I'm going to find maybe one of these ending structures, this antimony O2, this MP230. We can, instead of performing kind of the more complicated query that we did in the second piece of our activities, we can just say, rester.query, and we can just give it the unique material property ID, and then maybe some material properties that we want to extract out of it, like the band gap or the final crystallographic structure. So we can hit Shift-Enter to run through that cell. And now what you've returned are all the periodic lattice sites, the band gap of the material, and this is sort of done now on the fly in the Python script. Anytime you go to the materials project database, let's say we wanted to look at this antimony O2 compound. I can find antimony. Okay, let's look at cobalt since that's the one I found first. All these structures, like I showed before, have this crystallographic structure associated with them. So you can go to the Materials Project website, you can click through all the atoms, or you can do something that's a little bit, more quicker, a little bit more on the fly. Okay, so now we can do this again for a ternary case, where we're again going to loop through all these combinations of 3 that we created, and now we can create ternary phase diagrams out of our combination of 3 elements. So before, we noticed that antimony and silver did not form a stable compound, but antimony and cobalt did. And we'll see that there isn't a stable ternary in this specific subset of elements. However, it does look like cobalt and silver can bond with an oxygen atom to create one stable ternary phase based on these DFT calculations. Now it's going to go through and do this 2 more times for other combinations. And while we wait, we're going to basically say, okay, this is the same block of code that we saw before for the binary example, where I've just stored all of our IDs in a separate dictionary that we can then use to query later. Now we can see here this cobalt oxygen antimony is a little bit more messy, and we have 3 stable compounds in here. And then eventually what we'll find as we run through all this, we can do the same thing now for the quaternary phase. It'll create a little bit more of a complicated diagram that with all the lines kind of connecting together, it's a bit messy to see. There are options that you can go into to change sort of how much information these diagrams give you. Most of the code that's shown here is kind of the default out of the box from their example codes. So I wanted to kind of create this as an example for this workshop that shows maybe some of the experimentalists in the room how easy it is to get some of this calculated data. So while these are thinking, we're going to wait for our final structure to get pulled out. But that's basically the gist of it, is, again, by performing these simple queries, we can grab now phase diagram data, and once you're happy with some of the structures that you've grabbed from the materials project, you can do secondary queries for any of those properties that we showed before, like mechanical properties, XRD patterns. For this example, there isn't elasticity data, but you might be interested in piezoelectric constants or dielectric constants. So there's a wealth of information that's available on this database, and by kind of marrying a lot of techniques together with point-and-click GUIs and query operations through Python scripting, we have a lot of tools at our disposal to explore these different materials and figure out which one we might want to make or to understand why it behaves a certain way. So with that, I'll open things up for questions round 2, if there are any more questions. Again, if you feel like you didn't want to ask any of the questions in the public chat, or you think of a question tomorrow, feel free to email myself or any of the other members of the team, and I'd be happy to take any additional questions if you're here. And for those of you that did stay, thank you again for staying. I understand that times are stressful right now, and so we appreciate your feedback and coming and staying for the extra time.
Zach, hi, this is Juan. Thanks so much. What do you recommend would be a good way to kind of merge experimental data with, say, databases like the Materials Project, where if you think of it, as far as I understand, the constants like the electric constant is calculated from DFT, but if you have more clear experimental data, how do you merge the actual data? Is there a simple way or an easy way, best practice?
I would say that's going to be very up to the kind of data that you have. So you might use one of these query operations to grab data from the materials project, and that would be all calculated data like piezoelectric constants. But then maybe there's an experimental data set on the Citrine database that you think you can use. You can basically pull any of the data from Materials Project. You could convert it into a Pandas data frame, and then you could also pull a secondary Pandas data frame from Citrine. There are operations that would basically be a concatenation of the two, and you could merge the two in that way, if that answers your question. But I think at the end of the day, that's going to come down to sort of a data management question of, I have a data piece from one area, and I have a data piece from another. I can either keep them as, say, separate Excel files, or you can merge the two of them together if you're trying to plot things with comparisons.
Yeah, it was more about the concatenation. Thank you.
Other questions for Zach? And again, I would stress that if you're kind of new to this or you're getting your feet wet, you can always use the tools that we have as starter codes and modify them to your wish and your needs. And then when you feel comfortable enough, you can jump into your preferred development environment, integrate everything with your data and go as you please. But if there's nothing else, and I know we are about 10 minutes over time, like everyone who's still here, to thank Zach once again for the effort.
Thank you.
Thank you.